Okay, great. Thank you so much for the invitation to be here. I got to take the longest single flight of my life. And actually the person sitting next to me turned out to be very excited to have 16 hours to ask a physicist everything he'd ever wanted to know, including when we would finally solve the problem of time travel. And you know, I said, actually, it's funny you should ask that because I'm actually, let's see, can I flip these slides? I said, it's funny you should ask that because I'm actually about to give a talk on the theme of going back in time. So I've sort of, you know, given up on doing this in day-to-day life. But I do have this dream that in some of these well-controlled quantum systems that we're able to build these days in the laboratory, this is a topic that we can begin to explore. Because after all, going back in time is just switching the sign of the Hamiltonian. So going back in time, why would you want to do this? Well, there are a couple of reasons having to do with the fact that, let's say I have some quantum many-body system that I'd like to understand. One way that you can maybe learn something about it is by asking whether, if I try to do this, evolve forward and backward in time, but there's some small perturbation in between, how close do I come back to my initial state depending on the size of that perturbation? Right? If the system is very chaotic, for instance, then a small perturbation will prevent me from doing this. On the flip side of that, if I have a system that I understand very well, and I understand how it responds to small perturbations, then this can actually give me a way, asking whether the system comes back to its initial state or not, of detecting a perturbation. And so this may have some applications in sensing and precision measurement. And so I want to talk about both of those angles today. Both of these are questions that you can sort of ask in a very classical setting, but I particularly want to ask in the setting of quantum mechanics and situations where you might ask, what role does entanglement play in all of this? And the second question that certainly at this meeting you might be asking is, this is all well and good in a closed system, but in reality, this ability to go back in time might be hampered by the fact that there's some coupling to the environment. And so is this concept of, you know, sort of approximate time reversal, let's say, still useful in an open quantum system that we might realistically be able to build? Okay, so I will, as my kind of model system for exploring those questions throughout this talk, the model system I always have in mind is one where I have actually a system of atoms in an optical cavity, and the interactions are actually interactions mediated by light. And this is a nice system for a couple of reasons. One feature of these light-mediated interactions will be that there's a straightforward way of switching the sign of the interaction. Generally, these are interactions that are easy to turn on and off, ideal for studying dynamics. We can have in Cavity-QED systems actually a very good quantitative understanding of the interaction to decay ratio in the system. And one other particularly neat feature of interactions mediated by photons is that the interaction can be non-local in character. So that can be useful for having a way of entangling many atoms in a kind of a massively parallel way. But potentially also is a way to building quantum simulators for sort of unusual phenomena. Much work has been done thinking about spin glasses in this context, and at the end of my talk, I'll speculate a little bit about some connections to black holes. So the outline, again, I'll start by sort of introducing these photon-mediated interactions and an experiment that we're building up to be able to study them, and then talk about two applications of this echo concept in precision measurement and in studies of chaos. Okay, so first of all, what do I mean by photon-mediated interactions? How can we use photons to make atoms interact? Or throughout my talk, I'll be thinking about spins, so two-level atoms. Well, there's a scheme that you can keep in mind is the following. So let's say I'd like to have some way of having kind of pairwise spin flips mediated by light. Then one way to do this is to say, well, what I'd like to be able to do is have a process where I drive my atoms with some control field that can, such that an atom that's in spin down can absorb a photon, flip its spin up, and in that process put a photon into the cavity, which another atom can rescatter flipping its spin in the process. And this can generate kind of correlated spin flips of pairs of atoms. And so one can get, if I sort of consider all the possible terms, I would have an S plus term that's two spins flipping up, S plus S minus. And if you add all these up, you get sort of an SX interaction, so an Ising type interaction with a couple of neat features. In principle, this is very versatile in that if I spatially address, I could control which pair of atom interacts. An important aspect of this four-photon process is that in order for it to be in sort of a coherent regime, what I'd like is that the process where a photon goes into the cavity is just a virtual process that's off-resonant. And the resonant process is the pairwise process. So there's a detuning there, the sign of which actually controls the sign of the interaction. So just by changing the sign of a detuning from cavity resonance, this is an interaction of switchable sign. And lastly, there is a regime where this interaction can be coherent, and it's the regime of strong coupling that you also heard about this morning in the context of optomechanics. You've heard about this a few times now. So this is the regime where the vacuum-Rabi frequency characterizing the atom-photon coupling in the cavity is strong compared to the characteristic decay rates, both leakage from the cavity or spontaneous emission from the atom. Okay, so we are set up an experiment that's designed to be able to access sort of the combination of features you'd like to be able to fully explore these photon-mediated interactions. So that combination being strong coupling, but also good optical access so that we can get in there and control the way that these atoms interact. And so it turns out actually to be a bit of a challenge, because normally what one does when one thinks about trying to engineer strong coupling is to make a very small mode volume to achieve a high vacuum Rabi frequency. And so what we said, we don't just want to make a tiny cavity with a small mode volume, because we'd like to be able to address these atoms. And so we decided to access a rather tricky regime of Cavity-QED, which is instead to focus on actually having, well, a small cross-section of the mode, so a small waist. So this is going to be one important thing in the strength of the coupling, having the waist be small relative to the atomic cross-section, lambda squared, but nevertheless have the mirrors far apart, okay? And so the goal is sort of having a waist around 10 microns, but having the mirrors 5 centimeters away, and the only challenge about that is that it's very near the edge of stability. And so what this actually looks like, this is our cavity in the vacuum chamber. There are some piezoelectric positioning stages to be able to actually align this after baking the whole thing. And so there's some flexibility to fine-tune the length of this thing. As one gets closer and closer to that concentric limit, the waist gets smaller and smaller, and at fixed mirror finesse, this cooperativity figure goes up and up. With the best mirrors we ever tested, this was over 200. The mirrors currently in the cavity, it's around 50, which we're still very happy with. That puts us deep in the strong coupling regime. So that's just to kind of show a little bit more about what this looks like now. There's an optical lattice in the cavity mode where the atoms are trapped. It's an image of the atoms trapped in the lattice. And when we trap them there, we can also see, for instance, by probing the cavity with some off-resonant light, there's a dispersive shift of the cavity resonance due to the change in index of refraction from these atoms, similar to what Michel was using to measure his superconductivity. So that's the current status of this experiment. We're looking forward to making these atoms interact. And I won't show you anything there yet. But we actually know something about what should happen in a simple limit, which is the one, the simplest limit to think about for the system is the one where all of the atoms are sort of globally equally coupled to the cavity mode. And there I can just actually sort of reduce this Hamiltonian, this SX Hamiltonian, to a Hamiltonian in terms of a single collective spin. That's just the sum of all the spins added up end to end. And so I can kind of represent that as a vector on a large block sphere of radius n/2 for n spins, or more precisely, not just a vector, but some fuzzy quasi-probability distribution that accounts for the noise of the quantum state. And this Hamiltonian is actually well studied because the first thing it does is to create a rather useful type of state, namely a squeezed state. And so you can think of this as just a Hamiltonian that gives an SX-dependent precession about the x-axis. And so what starts out as a circular uncertainty region gets sort of twisted by the fact that the precession is higher, precession is faster for positive SX, slower for negative SX. So that Hamiltonian has been studied actually in a number of different physical systems, in Bose-Einstein condensates, where the interaction is a real direct collisional interaction, in ion traps, where the interaction is a phonon-mediated interaction, similar to the photon-mediated one I showed you before. And it's also actually something that I've studied in Cavity-QED experiments in the past by a slightly different scheme than the one I showed you before. So just in sort of full disclosure, I showed you one way of making spins interact via a light field. It's not the only way. So I kind of showed you a scheme where you could, in principle, have very versatile control and spatial addressing. There's actually an even simpler scheme that just involves driving the cavity mode itself. And the essential idea is that if I set things up so that that dispersive shift of the cavity resonance that I showed you before is spin dependent, then I can get a situation where I'm driving the cavity, but the resonance depends on the states of all the atoms. The amount of light in the cavity depends on the states of all the atoms. And that light acts back on the atoms via an AC Stark shift. And consequently, that gives rise to an SC-dependent precession rate on the Bloch sphere that can give rise to these same twisting dynamics. Okay. And so that's something that we actually did a number of years ago. And it's actually rather interesting looking at the types of states that emerge from that interaction. This is kind of one can prepare these states, rotate them in different ways to measure the noise along different directions. And if you reconstruct what they look like, there's sort of these ellipses here for various amounts of light scattered into the cavity. And if you look at it carefully, you'll see, well, there's some squeezing going on, but also the area of the state is growing. And that's kind of a manifestation of the fact that, well, this is an open system. There's some light leaking out. There's some information in that light. And so I should point out, this was done in a regime where that cooperativity parameter is less than 1, about 0.1. So that's kind of a couple of orders of magnitude below what we currently have set up to do. But even in this regime of sort of relatively weak interaction, this is something that gives rise to useful entanglement in the sense that, well, one way of saying it is if you look at these states, their area is growing, but the narrow direction is still narrower than what it started as. And another way of seeing it is that, well, you can literally take these states and use them in spectroscopy to do better than you would with an unentangled state. And so this is something that we were able to use to improve the precision of an atomic clock by a factor of the stability of an atomic clock by a factor of 3. So it gets the same uncertainty 3 times faster than you would without entanglement. And by now, this has been actually, in a slightly different approach to light-mediated squeezing, been pushed to the level of a factor of 10 improvement in the atomic clock. And so this is something that is, I should, just to put it in context, part of a larger, very successful effort now at engineering quantum states that can enhance clocks, atom interferometers, precision measurement devices, magnetometers, by entanglement. So this is just an array of different results at various sort of regimes of particle number, down from small numbers of ions up to huge numbers of neutral atoms, and the vertical axis showing various amounts of metrological gain. And there are a couple of different directions that the community is pushing to advance this entanglement-enhanced capability even further. So one direction that one can try to go is further absolute precision. So just say stronger and stronger squeezing and larger particle number. But another direction that I actually find very interesting is asking what one has to do just to get closer and closer to the fundamental Heisenberg limit in a quantum enhanced measurement. And so I want to say a little bit about the effort to kind of push toward even an interesting direction on this plot is how can I get keep the same precision and use fewer and fewer atoms. And if I can do that, then I can, for instance, distribute my resources to use the additional atoms available to me to enhance the bandwidth of a sensor or its spatial resolution. So what does it take to get closer and closer to the fundamental limit? Well, the fundamental limit if one is taking the example of measurements of time, if I want to do the most precise measurement of time I can, I need a state with maximum uncertainty and energy. And that's this very non-classical Schrodinger cat state, right? A macroscopic superposition of something like all spins pointing up and all spins pointing down. So the question that you can ask is, first of all, what would it take to make and detect these states in some way that's scalable to large ensembles of atoms? But also, are there easier alternatives? Okay, so if you'd like to make these states, well, one thing I kind of dream of when I think about these photon-mediated interactions is that they could give a way of, say, coupling a single spin to an ensemble and mapping some superposition of the single spin to the ensemble via the light field. Or one can think about this interaction Hamiltonian I showed you before. It turns out this is also something that actually gives rise to macroscopic, to Schrodinger cat type states. This has been done in ion trap systems of up to about 14 ions. And it turns out, so if one twists long enough, there are interferences that eventually give rise to what started out as a spin pointing along this direction, turning into a superposition of the spin pointing along the front and the back of the sphere. So that's been done in systems of up to 14 ions. The challenge in scaling it up is, well, number one, it requires this very extreme strength of twisting, right? We need all these interferences to form and give rise to precisely this state. And the more and more atoms I want to do this with, the more the probability is that somewhere along the way I'll lose one and the whole superposition state will collapse. So that's hard, reaching this very strong twisting strength. And these states also become harder and harder to detect in the sense that what gives these states their sort of benefit for spectroscopy is that there's some very fine interference fringe, it's sort of these red and blue stripes here, that takes single atom resolution to detect. And this issue of detection is actually one that is quite general in quantum enhanced measurements. In fact, in any precision measurement. You'll never sort of do better than your detection apparatus. And so just to illustrate that, here are a few different kind of quantum states that have been used for measurements enhanced by entanglement, or in the first row, your standard unentangled state. And if you sort of take the standard sequence of Ramsey spectroscopy, which is sort of prepare a state with a well-defined phase in some direction, let it process, and then try to determine the phase by, well, measuring, doing one last rotation and measuring the spin projection of the state, then you can ask the question kind of how well does this spectroscopy do if I have some finite resolution of my detector? So the blue curve is answering that question for the unentangled state. It's sort of the 0 is the standard quantum limit, and eventually, if the measurement resolution is very poor, maybe the state you do worse. If you have a squeeze state, you can do significantly better than with the unentangled state, up to where your detection resolution is kind of similar to the noise of the squeeze state, then you start to benefit less from the squeezing. But if you have something like this Schrodinger cat state, then actually at some point, if your detection resolution is on the order of 1 atom, it's even less useful than the unentangled state. And so that kind of raises the question, is there something better one can do than just directly trying to detect this entangled state? And that brings me to the kind of echo idea that was on the first slide. So what happens if instead of directly trying to detect this entangled state, we let it evolve, perturb it a bit, and then ask whether we can sort of reverse the evolution back to the initial state? So we asked the question, actually, what happens if you do that with precisely this twisting Hamiltonian that's realized in so many physical systems? So you imagine I twist this state, I perturb it a little bit. In this particular case, the perturbation I'll have in mind will be a small rotation about the y-axis in this plot. And then I'll ask what happens after I kind of untwist, right? Apply that same Hamiltonian with the opposite sign. And well, what happens is actually rather interesting. So the perturbation basically shifted this state up a little bit in z. In this case, I have an sz squared Hamiltonian. The untwisting process turns that slight shift in z into a large displacement in y. And so it gives kind of an amplification. which should be useful for detecting this state. And another thing you can see is that basically it amplifies my signal, which is that small rotation, and it amplifies my quantum noise, so that the state I'm trying to detect is no longer has this very fine feature. It's something that should be much easier to detect. So just a little bit more schematically, if the sphere is confusing in kind of a planar approximation, what we've done is we're trying to detect this small vertical displacement, and this twisting basically shears it out into a large horizontal displacement. And the amplification by that shearing essentially tells me how much I should be able to win beyond the standard quantum limit, because the noise is essentially the noise of the unentangled state, but the signal has grown. Okay, so what actually happens if one does this? Well, first of all, for reference, let me show you, it's worth looking at this blue curve. So this blue curve is just saying, as a function of how strongly I twist in this step, what is kind of the intrinsic metrological potential of the state? And so the way out here is where you've prepared that Schrodinger cat state that gets all the way up to the Heisenberg limit. Somewhere back here is the sort of strongest squeezing you could get by that same interaction. And then there's actually a long plateau where the state is almost as good as the cat state intrinsically, but it's not actually, if you were to squeeze, you would never actually get this much squeezing. So it turns out if one does this echo scheme, the metrological gain goes almost to this plateau, so actually very close to the Heisenberg limit. The state is doing better than a squeeze state would, so this is actually a non-Gaussian state that's sort of starting to wrap around the sphere. And this echo gives actually a nice way of sort of harnessing even that non-Gaussian state in a precision measurement. And so now if one sort of asks, how well does this do as a function of resolution in state detection, this gives a substantial benefit getting almost to the Heisenberg limit, with a fixed numerical factor, even at the point where my detection uncertainty is on the order of the square root of the number of atoms, so really a large detection uncertainty. This is all kind of an idealized picture of perfect unitary dynamics. If one has some dissipation in the system, then that will modify exactly which state I prepare, like in the picture I showed you where those squeeze states are broadened a bit. But the essential benefit of this echo scheme in terms of making it much easier to detect the same state holds. And so over kind of a wide range of parameters in terms of the cooperativity parameter of the cavity and the number of atoms involved, this gives a substantial metrological benefit without any need for sort of optimizing a very sensitive coherence-preserving measurement. And so this is something that we were actually happy that our colleagues right down the hall in Mark Kasovich's group had just the right sort of setup to try this out. There's a precise implementation is slightly different from what I showed you, but the essential concept of this interaction-based readout is something they were able to show. And in particular, to detect states squeezed by 8 dB with just a low resolution fluorescence measurement that would not have resolved the quantum noise of an unentangled state. So that is kind of the state of the art in this interaction-based measurement. And I think one exciting direction is really pushing this to the point where one can actually do this with these over-squeeze states that can approach the Heisenberg limit. And there are a few different physical systems that are promising for that. We may explore this in a strong coupling cavity. One other one I just want to highlight that looks very promising is actually one with atoms in an optical lattice that are interacting via coupling to Rydberg states. And I want to mention this because in contrast to some of the other forms of interaction I talked about before, photon-mediated interactions, the interactions in ion traps, some systems naturally have this all-to-all interaction. But I think there's an interesting question of what happens when one explores a system where entanglement actually needs to spread over, where there's a finite range of the interaction, and you have to ask, how does entanglement spread in a spatially extended system? So we sort of thought about the very simple limit. If you confine these atoms to interact within the range of their interaction, this already looks kind of very promising for reaching the point of having sort of 200 atoms doing a measurement that you'd normally need 10 to the 4 atoms for without entanglement. But there's reason to believe that if one sort of does takes a more sophisticated approach and says not only how much entanglement can I generate within the interaction sphere of a single atom, but allowing an entanglement to spread over the whole system, maybe there's actually even more to be gained. And so I think it's an interesting question whether this type of echo method is a way of kind of accessing some hidden entanglement for using it for precision measurements. But it also raises the point that there's broadly a broader question is one of sort of how does entanglement actually spread in a many-body system? And that's also something where this, what I'd like to argue that this kind of echo idea is something that's useful for probing that. And so the sort of next part of my talk, what I want to ask is actually, I want to start with a very simple question, which is the following. So suppose that you have some extended quantum many-body system. You have some information encoded in a particular spin or qubit here. The question is, how long does it take for that information to spread over the entire system? So, sort of, schematically spreading over the yellow region here. So it turns out, I first heard about this question from people who were, I thought I would never be talking to, people who were thinking about the information problem in black holes. And so you might ask sort of how are people who spend their time thinking about black holes connecting that to quantum mechanics at all. And the connection in a kind of very schematic and hand-waving picture is the following. So essentially, if one has some quantum system like the one I drew in, let's say, d spatial dimensions, and you try to understand kind of the low energy properties of that system by a process of renormalizing the degrees of freedom in a way that sort of coarse graining the system in a way that preserves as much as possible the structure of entanglement. That renormalization process gives rise effectively to one more dimension, and there's a duality that comes about where this d-dimensional quantum system starts to look like a d plus one dimensional classical field theory, which in certain cases has actually the kind of the geometry of a black hole. And so the question that this kind of raises is, are there actually quantum many-body systems realizable in tabletop experiments that under this duality actually map onto black holes? And if there are, how would we know? And so one way that you might know is actually by asking about how information is scrambled in the quantum system. And the reason is that there's a rather well-founded conjecture that black holes, or the systems dual to black holes, saturate a fundamental bound on how fast information can be scrambled in any system. And so the bound is the following. So the idea is there's some time scale, we'll call tau, that's the time for local observables to equilibrate. In the black hole case, this would be set by the inverse of the temperature. And the claim is now that the time, though, for information to spread over the entire system is going to be larger, right? It needs to not just equilibrate locally, but spread over the whole system. And at best, so in the very fastest case, it will be larger by something that's the log of the entropy of the system. So you can kind of get an intuition for where that should come from by thinking of a toy model of n qubits, or where the number of qubits is essentially what sets the entropy, right? It's the log of the Hilbert space dimension. And the qubits are allowed to kind of interact in pairs on this time scale tau. And so you'd say, well, if I want information to spread really quickly, what I can do is kind of in each time step connect each of these guys to a random partner, and then reconnect them and reconnect them again, and so forth. And in each step, information will kind of spread from 1 to 2 to 4 to 8 of these qubits, and the time to spread over the whole system will then go as the log of the total number. So that kind of suggests that if one wants to find a system that would saturate this bound, it's natural to look at models that have some kind of non-local structure of interactions. It also suggests that I'd like something chaotic, so that information can spread fast. So that kind of raises the question, well, how do you even define and quantify chaos in the quantum system, right? my classical notion that somehow trajectories should rapidly diverge doesn't apply if I try to measure the distance of the quantum system by some overlap between quantum states. So it's been pointed out that a natural way of thinking about chaos in a quantum system is to still look for some kind of a butterfly effect. That's something about how a perturbation is spreading. But it's a butterfly effect in the commutator between two simple operators. So for example, let's say I have some spin chain. What I'd like to know is something like, if I perturb a spin over here with this operator W, how long does it take for the influence of that perturbation to spread over here such that this operator W at a later time no longer commutes with the operator V, right? Initially they should commute, they're just operations on different spins, but interactions in the system might make them fail to commute over some period of time. So what one would like to measure is this commutator between initially commuting operators as a function of their separation in time. And so that's, I can think about measuring the commutator, or I can think about measuring the overlap between quantum states where I've either applied the operators in their standard order, so first V and then W at this later time, or applied the operators in their reverse order. So this is called an out-of-time order correlation function. It's sort of a fancy name, but essentially what it's really saying is it's a way of, it quantifies the overlap between two possibilities. One, I start with some initial state, I apply this operation V, I evolve forward in time and apply the operation W, or I start with this initial state, I evolve forward in time, apply the operation W, and then go back in time before applying the operation V. So sometimes I like to think of this as the upper branch here being the situation where I gave this talk with all of the slides in the correct order, and the lower branch being the one where I skipped a crucial slide at the beginning and then realized it and went back, flipped all the way back to give it to you again. And if I realized it sort of pretty quickly, then that's, you might not be too confused, but if I take a very long time and then go back, by the end of the talk, you'll not be so happy. And what I want to measure is kind of the overlap between the happy you and the confused you. And so the kind of ingredients that it seems one needs to measure this are some way of going back in time, switching the sign of my Hamiltonian, and some form of many-body interferometry that lets you measure the overlap between two quantum states. Okay, so with my collaborator Brian Swingle, we thought a bit about how one would actually do this in the most general case, to do some kind of many-body interferometry, and there's a nice scheme one could use if one has a control qubit that can control when I apply this operation V. But actually, it turns out for certain cases, for simple initial states, for instance, there are actually simpler schemes that require this ability to go back and forth in time, but not extra ingredients like a control qubit. So there's actually a very nice experiment that's been done in the group of John Bollinger with Anna Maria Ray, showing how one can measure actually these out-of-time order correlation functions by something that actually looks very similar to the echo scheme I showed you before, with one slightly different rotation in it. And so in fact, we're measuring these out-of-time order correlation functions for precisely this twisting Hamiltonian. And it turns out, actually, these experiments are inspired by ones done decades ago in NMR systems. So this is a method called multiple quantum coherence, and actually, if you go back to NMR papers from the 1980s, you can see that they were thinking about very similar questions of how a perturbation spreads over a network of nuclear spins. So I was actually kind of fascinated to see this picture that maps onto what I thought was something new coming from the black hole community. So bottom line, this is something that's measurable. And so one of the questions that we were asking in parallel with asking how would you measure it is actually what would you expect to see? So this so far was not in a chaotic system, but you can think about, there's a kind of the sort of first natural chaotic model you could extend to from these twisting interactions is something called a kicked top, which is a system where one stroboscopically alternates between this interaction term and a spin precession. And this is a well-studied model, and one of the things that is known about it is that, roughly speaking, if you want to ask how long does it take for the kind of this quasi-probability to spread over the entire space with this block sphere, then you can think about the fact that, well, you start out in a coherent spin state, which occupies an area that's about 1 over n of the sphere. And so if it grows exponentially, then the number of kicks to grow over the whole sphere should be something like the log of n. So we have some intuition from this kind of quasi-probability picture, and we kind of ask the question, what does that, how does that map onto what one would see in these out-of-time order correlation functions? So first, for reference, this is just a time-ordered correlation function. So a simpler, only 2 operators involved here. And what one sees if one looks at the decay of this type of correlation function in time, I've plotted it here for various atom numbers, so kind of scaling up the system size. If anything, as I increase the atom number, it decays a little bit faster than at small atom number. In contrast, if one looks at this out-of-time order correlation function, the time scale for the decay grows the larger you make the system size. And this is kind of makes sense as a signature one would look for in something that's supposed to show information kind of spreading over the entire space. And so as the space is becoming larger, this grows. And the time scale growth in the time scale, it's roughly consistent with something logarithmic, as one might expect from this picture of seeing some kind of butterfly effect on the block sphere. One question we asked is, this is all well and good in the idealized unitary system. Could one hope to observe something similar with realistic dissipation? So first of all, what I like about seeing this growing time scale is it looks rather different from what I would expect if for a decay that's just due to coupling to the environment. So that's already nice as a signature of something that one can look for that tells us, yes, this is really something about the scrambling behavior. But my student also did some nice quantum trajectory simulations to ask the question if one sort of does this with realistic, difficult to achieve, but realistic cavity parameters, and asks what does the dissipative evolution do compared to the unitary one. The dissipative one is the dashed one, and at least qualitatively, it displays quite similar behavior. I would love to know what happens as this becomes more and more dissipative. It turns out it's hard for us to calculate. So that's all theory. We were actually excited to see, though, that there was an experiment done just very recently, showed up on the archive, where this kicked top was implemented in a BEC system. The spin is formed from momentum states of the BEC, and they were actually able to start measuring these out-of-time order correlation functions and comparing with theory. So this is, as far as I know, the first measurement now done in this kicked top system. One question that I want to briefly ask, just to sort of, first of all, make sure we're on the same page, is I showed you it looks like the scrambling time has sort of this logarithmic scaling with the size of my block sphere. So is this a fast scrambler? I said something about, what this fundamental bound is, this fast scrambling bound. Does anyone have a thought on that? What was that? I heard it. Did somebody say no? So, do you want to comment on it? No. So, I'll answer my own question. So, this kind of superficially looks a little bit like what I showed about that fast scrambling bound, and I want to emphasize that I don't claim that this is something that is saturating that bound or behaving like a black hole. There's a key difference between this system and the sort of toy model of n qubits I showed before. This one is not in a 2 to the n dimensional Hilbert space. This is in an n order n dimensional Hilbert space. It's restricted to this collective spin block sphere, right? So this is, this is something where the time scale scales with the log of n, but the Hilbert space is not nearly as large as in the true sort of many-body case that's really of interest. So one of the things that I think is an important question is, how does one go beyond this kind of effectively single particle physics, right? The physics of just this large collective angular momentum vector, to can one actually have more complex non-local interactions mediated by this single mode of light that would allow us to really explore something more akin to these exotic models for fast scrambling. And so that actually raises the question, right? Can a single mode of light actually mediate more complex interactions? And there are a couple of ways one could go about this. One could think about literally having some time and spatially dependent control fields to do a sequence of random gates like what was shown in that diagram before. But it turns out there's actually a more elegant approach that we're actually very excited about pursuing in my lab, to have kind of rather versatile control of long-range interactions in a single mode cavity. And so the idea is essentially to be able to realize a class of models that look something like this, so some sigma plus sigma minus kind of flip-flop interactions with control of the strength of the interaction versus distance. And one thing I like about this class of models is I can kind of think of it as some spin excitations that are sort of hopping, right? So I can think of this as flip-flop processes between the spins, or I can map spin up onto a particle on some site and spin down onto no particle on some site on the site, and I can think of this as essentially a model of hardcore bosons hopping. And the neat thing is that there's, in fact, an elegant scheme for dialing in what the hopping matrix elements are. And the idea is essentially to impose, in the spin system, a magnetic field gradient that gives me a way of, first of all, kind of turning off the all-to-all hopping that one could sort of most easily implement, and then controllably restoring hopping at select distances with control fields whose frequency difference is tuned to that difference. So basically, a magnetic field gradient gives me a way of controllably engineering hopping processes at a well-defined distance. It's a little bit similar to something that is done actually in optical lattice experiments to engineer synthetic gauge fields in optical lattices by controlling for instance, the phase of the nearest neighbor hopping. But in this case, it's a situation where, in principle, one can kind of imprint a very flexible control, imprint essentially arbitrary control of the hopping even at long range, mediated by the cavity mode. And rather elegantly, actually, the dispersion relation for a single spin excitation ends up just being determined by the waveform in which a single control field is modulated. So you can imagine doing kind of crazy things that you would never find in nature, like saying I'd like some system where I can have hopping of nearest neighbors, second neighbors, fourth neighbors, eighth neighbors, and 16th neighbors, so that information can propagate very fast. If you sort of were to dial in that particular dispersion relation, it would actually look like a fractal, which is kind of neat. If you randomize the phases, it would look like something very chaotic. And then you would ask, oh, maybe this is a good way of engineering the chaos that will give rise to fast scrambling. Now, one has to be careful because actually, as if I have a translationally invariant system, no matter how crazy looking the dispersion relation is, this will not be chaotic. It's a conserved quantity, quasi-momentum. But combined with some disorder, this actually can give a chaotic model. And that's one way of seeing that is by looking at kind of the energy level statistics. And as by looking at sort of the statistics of the level spacings in this model, one can see that it's chaotic, but one still can't see much about how fast information is scrambled or how fully it's scrambled. By looking at these kinds of out-of-time order correlation functions, one can. And it looks like in this type of model, there's actually a very interesting transition from the system not being fully chaotic, not exploring the full Hilbert space if one just has a single particle, but becoming more and more chaotic and scrambling more completely as one approaches the limit where this is sort of half filled. So half the spins are up or half the sites are filled with bosons. So is it scrambling? So it's scrambling completely. Is it scrambling fast? It's hard to tell with numerical simulations that can go up to only small numbers of spins. This type of model is something that I think is really an exciting direction for quantum simulations. And so just to kind of summarize this scrambling part of the talk, in some sense, this scrambling is kind of the ultimate form of thermalization in a quantum system, right? It's really asking how long does it take for information to spread over the full Hilbert space. But there are many open questions about kind of which systems scramble fully and how fast. And I think that these non-local interactions, particularly for the question of fast scrambling, offer a really exciting possible direction for exploring this in experiments. More generally, I hope I showed you that these echoes are a nice way, on the one hand, of probing chaos, and on the other hand, of exploiting sensitivity to perturbations for precision measurements. And with that, I just want to thank my research group, particularly also my collaborator, Brian Swingle, who taught me about scrambling and black holes. And with that, I will take any questions.
Okay, questions? So actually the level statistics problem, level statistics is a late time feature, right? Because you have to go to a very small H-bar energy resolution, which will only develop at a very late time scale. So the level statistics, if you are fully quantifying it, then that will be somewhere where the out of time order correlator has already saturated. So I don't know if the exponential growth part is not the where you can detect the full level statistics.
So I think maybe we're saying the same thing in different ways. The point I think is interesting is, at least to me, the level statistics appear like a fairly coarse measure of what's going on. And there are things I at least in my untrained eye, by looking at the level statistics, can't tell either whether the system will even fully scramble or not. Whereas
the level statistics is an artifact after the system has fully scrambled. So
yeah, well, at least for me, comparing sort of what I see in the level statistics with what I see in looking at these out-of-time order correlation functions, there's actually appears to be more information in the correlation. I mean, not surprisingly, certainly if one looks at enough of the correlation functions, there's more information just about even how much of the Hilbert space the system explores. Now, there are people thinking about things more sophisticated than just the nearest neighbor level statistics, right? So also sort of correlations at larger energy spacings, and I think maybe that reveals something more akin
to engineer. So
yeah, so I think that it's generally true that one makes trade-offs. So so there's a question: are you more sensitive maybe to the perfection of the reversal of the Hamiltonian, or maybe of any other rotations that are involved in the sequence? So first of all, the gain is not exponential, and so I think there's also not an exponential trade-off. In kind of the obvious things that we thought about in terms of what control precision does one need, there's not something obvious where it's that would stop working. But I think there are always trade-offs, and it's kind of a question of this gives you some more freedom to optimize among those trade-offs. And something nice that actually was done in the experiment by Oner Hostin and Mark Kasevich was to think about what is kind of the optimal amount of gain of this sort of gain in the interaction-based readout in a given sort of experiment. And they actually kind of showed that depending on how strongly squeezed their state was and what their detection noise is, there's some optimum in terms of how strongly they apply this twisting Hamiltonian for the detection.
Monika?
Yeah.
So in the nice comparison you drew between the spin systems and the black holes, I didn't really understand what constraints, because you talked about the temperature of the black hole and its size, but there is a relationship between the entropy and the temperature of the black hole. So how does this factor in this fast scrambling?
How does it? Yeah.
Before there was when you drew this analogy, yes. So there was this temperature, and I think it is.
Yeah. So I mean, so the idea is that the temperature is what sets.
Yes. So,
kind of
so there was the relaxation time,
yeah.
which was in fact dependent on the temperature of the black hole, and there is the scrambling time.
And there's the scrambling time, which is
so. But the temperature and the entropy of the black hole are related.
Related, but the mass also comes in there, right?
Mm-hmm.
So they're not unrelated, but it's the entropy that then sets sort of how much longer compared to the temperature, compared to the time scale set by the temperature, should it take for the information to be fully scrambled.
Because the entropy is related to the area of the black hole.
Yes.
But that's also related to the mass. So it's
exactly.
it's related to the temperature also.
So the idea is somehow the larger the area, the longer this scrambling time will be. But you're right, there's a relationship with the temperature. So first there's a time scale that's just set by the temperature.
Mm-hmm.
And then there's this additional factor that's
Okay.
set by the entropy.
So in the end, you would have a scrambling time which would be a bit like something like the entropy times the log of the entropy, a sort of.
You're saying if I now re-express the temperature in terms
Yes.
of the entropy,
Yes.
then I think that's right, and I probably have to sit down and think about it because I'm more used to thinking about the qubits than the black holes. But I think you're right that
So in the
if I
end,
express it either in terms of the temperature or the entropy, it will
yes.
look less simple than this. Yeah, I think that's fair. Yeah.
Okay.
So this is about the last part of the talk where you said that you could engineer maybe finite range interactions with a single mode cavity, right? Like there are no multiple modes, but atoms in a cavity, and then you could somehow engineer
Yes.
finite range, not
Yeah.
infinite range, which
Yeah.
is the use. So could you comment a little bit more, because I didn't catch what else do you have to do exactly in a cavity implementation to make this
Yeah, sorry, I went through
infinite
that a
range
little
into
bit.
finite range? Yeah.
The basic idea is that I need some way of, labeling my spins in a way that depends on their position. And so that's essentially applying a magnetic field gradient. And so now, if I want to engineer an interaction between spins at a particular distance, it's going to involve one of these 4 photon processes, but the frequency difference involved to make it resonant will depend on the difference between the spins, the distance between the spins. And so now, by setting the frequencies of control fields with which I drive the system, I can set the interaction strength versus distance. So in particular, a particular pair of control fields separated by a given frequency introduces interactions at a specific distance.
Sort of introducing another length scale from the outside.
Yeah, essentially exactly. So from the outside, I'm introducing a way of controlling the energy difference required for that flip-flop process as a function of the distance between the spins.
Yeah, here. I get a question about the experimental requirements over here.
Yeah. Oh, there, sorry, yeah.
Sorry. So to measure the correlator you define to get a hint on this scrambling, you need single-site addressability, if I recall, and also pairwise interaction between all the spins, right?
So
in your proposal.
Yeah, so one has some choice of which operators to use in measuring this correlator. And so I sort of drew a picture where it's local operators, and that is one thing that's natural if I'm sort of asking about information propagating from here to there. In the example I gave of the kicked top, the operators we were actually thinking about were global spin rotations, and in the measurements that have been done so far.
You don't need to measure each spin individually.
So you don't necessarily need to. So, but I think it is a nice thing to look at. In the kind of collective spin models, it's natural to ask about something like the magnetization or the sort of global variables. But certainly when one starts to think about how information is propagating in a system where the spatial degree of freedom matters, then I think single site or at least local addressability is a natural thing. And we're certainly setting up to have local imaging. It's not precisely single site.
Okay, so that was the next question. I don't know much about your system. I mean, I don't know at all. It's possible to have this cloud of atom, a cavity, and single site, being able to observe each atom?
You're expecting that once it's well optimized, our imaging will have 1 micron resolution, which turns out to be a little bit longer than the lattice spacing. But on the other hand, it's a system where we won't necessarily have 1 per lattice site. So roughly speaking, it's certainly local addressability. It's not optimized for single site, but
Because the cavity is like
and
straight.
the length scale of the atomic system is hundreds of microns per scale.
Okay, with that, let's, is there, okay, fine. Let's